In this video lecture, we want to practice analyzing some diode circuits. This lecture is part of a series on Introduction to Diodes from a circuit perspective. Here's the table of contents here where I've noted which lecture previously had covered which topic. Our focus for today is analyzing some of these diode circuits. So let me jump to a page with some problems. And our first problem involves a simple voltage source and a diode and a resistor. And we are told that Vs, the voltage source, puts out a triangular voltage that goes from minus 10 volts to plus 10 volts and back again. And we're asked to plot Vr of t, the voltage across the resistor here. We're not told specifically what the diode, any characteristics of the diode. So typically, if you're not given any characteristics of the diode, you would have to make an assumption that the diode voltage is either going to be, or the diode will be modeled as a 0 volt ideal diode. Okay, so it's either 0 volts when it's on or it's an open circuit when it's off. That's what I would do. You could also decide it's going to be a 0.7 volt ideal diode. In other words, it's ideal in every way, like it's an open circuit when it's off. And when it's on or conducting current, instead of being 0 volts, it's 0.7. So let me change the color of this to something else, and we'll draw the curve for each. Okay, so if we assume that it's a 0 volt diode when it's on, then all we really need to do is figure out whether the diode is going to be on or off. And this is where we use a method called a solution by assumed state. So what you do is you want to pick some condition. In this case, let's pick Vs equal to plus 10 volts. If we have plus 10 volts here, then we have to ask ourselves, is the diode on or off? And if we can guess one or the other, and then we check whether or not the resulting currents and voltages actually support our assumption. So for instance, here hopefully it's obvious to you that if Vs is at 10 volts and all we have is a diode pointing from the source to the resistor, that diode is going to be on and current is going to flow, in this case 10 volts divided by 1K, so 10 milliamps. Let's say though that you guessed wrong, or I guessed wrong, and I said, I think this diode is off. In that case, we would draw a circuit that would show the state of the diode, so it's off, and we would label our voltage VD here, and this is 10 volts, and we would have to solve then for the voltage of the diode. Well, VD would then be equal to what? Plus 10 volts, right? Oops, plus 10 volts. Now, if we have an ideal diode, 0 volt diode, we know that the diode curve looks like this, where this is current, this is voltage of the diode, right? And this is 0. So you can't ever have a positive voltage on the diode. You can't do that because as soon as the diode turns on, or any voltage that you put, any current that you put through it in the positive direction will produce just the 0 volts across it. So this cannot occur. Therefore, we guessed wrong. D must be off. Okay? So that's the idea of analysis by assumed state. So in this case, let's go back and assume that the diode is on. And if it's on, then we have 0 volts across it, and all 10 volts are across the resistor, and therefore we would have 10 milliamps flowing here. And now we have to ask the question, okay, does the diode VI curve support that? And the answer is yes, because you could be up here at 10 milliamps, it's positive, and there is a 0 volts across the diode when there's a positive current flowing, and that's exactly what we have assumed. The diode is on, there's 0 volts, all 10 volts go across the 1K resistor. So that is correct. I'm going to draw a point right here on our curve that when it's plus 10 volts, the diode will be on. Now, in this problem, it's pretty simple given what there is in the circuit, that if the voltage Vs should decrease from 10 volts to 5 volts, the diode would still stay on. Oops. Okay, and so we'd still have a short. And in fact, the diode is going to stay on for all, actually let me erase this and put my answer down here. Okay, down here. So we get, it's going to look like this. And the question is, what happens when the voltage source goes negative? Okay, so now if it's negative 10 volts, and we assume, I'm suspicious that the diode's off in that case, right? So if the diode is actually off, and if the diode's off, no current flows, and therefore no current flows through R, and no resistance is across R. So we have 0 volts across R. That means all 10 volts are across the diode. But the polarity is VD equal minus 10 volts. And minus 10 volts is over here, right, on the diode curve. And so that is consistent with the diode curve too. When you have a negative voltage, you have no current. And so now we can conclude that when Vs is negative, the diode will be off. Okay, so in this region here, D is on, shorted, okay. And in this region here, D is off. Okay, so that's our part A, problem or circuit A. Incidentally, if we were to resolve this, but where we assumed a 0.7 volt drop diode, then I won't explain it here, but you can think about this and should become obvious or apparent with a little thought that this shape of this curve would be shifted by 0.7 volts. Okay, so it would be shifted down by 0.7 volts. In other words, to turn the diode on, you have to get 0.7 volts across it. So if Vs is 0.6, it's not enough to turn the diode on. But once you get to 0.7, it turns it on. So there'd be a shift. Okay, now let's look at part B of this first problem, where we have the same circuit, but there's a 3 volt voltage source. In that case, let me draw this in red here. So we'll look at VR in red. And what we will find is that, let's consider the case where we have plus 10 volts. Okay, if we have plus 10 volts, again, I think you should be able to show that the diode will be on. However, instead of having all 10 volts across the resistor, we'll have 10 volts minus 3 volts across the resistor. And so the voltage on VR will not be 10, but will be 7 volts. So maybe I should make a copy of this and move it over here. Squeeze it in here. Okay, so this is going to be for B. So it'll be at 10 volts, it'll scale down to 7 volts. Okay, and if Vs, let's say, is 4 volts, then the voltage across the resistor will be 1 volt. And if Vs goes to 3 volts, then the voltage across VR will be 0. So we get this shifted curve that looks like this. Okay, and the peak is going to be 7 volts. All right, and this point here corresponds to Vs equal to 3 volts. Okay, let's look at example 2. Here we have a voltage source and a resistor, like a Thevenin network, and we're asked for the voltage across that Thevenin network, but there's a little caveat. We have this diode D1 in series with a 6-volt battery that is hanging across it. And we're asked again to plot a voltage, in this case V out. Now let's consider the case when Vs is 0. If Vs is 0, then what we really have is a resistor and then in series with this diode and 6-volt source. Okay, and the question is, can any current flow? If I were to draw a current here, what is that current? Well, the current cannot be negative because the diode only conducts current in one direction. So it would have to be a positive current. Is there any voltage source or current source in that loop that would tend to cause current to flow in the clockwise direction? And the answer is no. If it weren't for that diode, we'd actually have a current I equal to minus 6 volts over 1K, right? But the diode prevents it. So when you have Vs equal to 0, D1 must be off. Okay, D1 must be off. So I'm going to plot that point. So because if D1 is off and Vs is equal to 0, then clearly the output voltage is just Vs because there's no current flowing through R1. And in fact, you can show that that will be the case all the way up to 6 volts. Right? You can test this right at 6 volts. What is the voltage across D1? It'll be actually 0, and no current will flow through R1. But if, let's say Vs goes to 7 volts, let's draw that case. If Vs goes to 7 volts, and we have a resistor here, 7 volts, 1K, okay, then I'm going to claim that D1, and we'll check this, D1 is actually on, all right, and that would put 7 volts minus 6 volts equal to 1 volt across the resistor, and the current that would flow would then be 1 volt over 1K, okay, 1 milliamp. 1 milliamp would flow from the 7 volt Vs to the 6 volt battery through D1, and yes, that does confirm that D1 is on. And importantly, though, the voltage across the terminal labeled V out is simply the voltage of the 6 volt battery, right? Because the diode D1 is shorted. And so we would have 6 volts at the output. So what this circuit does is it actually clamps the voltage. It clamps the voltage to 6 volts. Okay? And you can confirm that when it goes negative, you know, the diode's not going to turn on. It only turns on when Vs goes greater than 6 volts. So this is a clamping circuit. All right. Let's look at part number B, or exercise 2B. Here we have the same 6 volt D1, but we've added a second diode D2 with a 2 volt. And I will just draw the result. But you try to figure it out. Maybe pause the video and think about it. Notice that D2 is in the opposite direction of D1. Okay, we'll still have the clamping at 6 volts. But now let's just think about this one case. What if Vs is equal to 0? If Vs is equal to 0, then you're going to have this R1, and you have D2 and 2 volts. And I'm going to claim that this is actually on and current is flowing. Basically 2 milliamps is flowing from the 2 volt source, causing D2 to be on. And if D2 is on, then the voltage at V out is actually the 2 volt source. So this is a clamping, kind of a two-sided clamper, okay, where it clamps the voltage between 6 volts and 2 volts. Okay, so even if the input Vs should extend beyond outside of 2 and 6 volts, the output will never go larger than 6 or lower than 2. Okay, let's move on to problem exercise 3. The question is, what is the voltage across R2? So in this problem, it's a static problem. We just have some DC sources, and we're asked to figure out, is it on, is D1 on, or is it off? Once we figure that out, then we can figure out, we can answer the question. So let me make a little more room here. Okay. So what do we have? Over here we have a Thevenin source, and what would make it helpful to solve this problem is if I could Thevenize this. Okay, Thevenize. So I'm going to use source transformation to make our lives a little easier. We can replace this with a voltage source and resistance, the resistance of which will be the same as the Norton resistance, and the voltage will be the Norton current, 3 milliamps times the Norton resistance, which is 4K, so we have 12 volts. Let me redraw the circuit here, and now it should become very apparent whether the diode is going to be on or off. So on the left side of the diode, I have 10 volts trying to push current through the diode. And on the right side, I have 12 volts trying to oppose current from flowing through the diode. And so actually the voltage across the diode here, VD, I'm going to claim is minus 2 volts, and therefore no current flows. And in fact, if no current flows, that is exactly the voltage across the diode, because there will be no current flowing through the 1K or the 4K resistors. So therefore, D1 is off. And now we can find the voltage across R2. Remember, we're asked for this voltage right here, V of R2. Well, if D1 is off, okay, then all we have is a 3 milliamp flowing into a 4 kilo ohm, producing 12 volts. And so, therefore, with D2 off, VR2 is equal to 3 milliamps times 4 kilo ohms. Sorry, writing too fast. 4 kilo ohms equal 12 volts. And so that is our answer. The voltage across R2 is 12 volts. All right, let's look at problem 4, which is a little more complicated. Here we're asked to find the current through ID1. Okay. Now, we're always looking for, when you're trying to solve a diode circuit by assumed state, well, in any case, but in this context where we're basically trying to figure out is the diode on or off, you want to look for ways to simplify the circuit. Source transformation, Thevenize, Nortonize, whatever is necessary to try to get the circuit into a single loop or a single node pair, or yeah, those would be the two that you'd hope to arrive at, and or at least particularly those if the diode is well, I can't explain. Let me just show you this example. What I see here is I see on this side, I see a voltage source, 2 resistor, voltage divider, and that can be Thevenized, right? That can be Thevenized. If I could get rid of the 1K that's grounded here, I would essentially have a single loop minus the presence of the diode D1, and I think I could actually, figure out whether the diode is on or off from that. So let's proceed to Thevenize this and just see where it leads. It certainly will simplify the circuit, right? So Thevenize, you're going to look in to the left here, and with the source off, and you see 1K in parallel with 1K. So I have a half a K here. And the open circuit voltage I would see is 4 times the voltage division ratio, which is 1 over 1 plus 1. So it's 2 volts, right? So this is what I have. I have 3K and 8 volts over here. Okay. Now, I'm thinking that I have this diode here that I'm going to call this node Vx. Okay. If I solved the circuit without the diode D1 in there, and I solved for Vx, if it turns out that Vx is less than 1 volt, then that would mean that the diode D1 would be off, right? Because the cathode end of the diode is sitting at 1 volt due to the battery. And so if Vx is sitting at a voltage, which is the anode end, if the Vx is less than 1 volt, then that diode is off. And I will be done with the problem. If Vx turns out to be greater than 1 volt, then I have to conclude, the diode is shorted, and I need to solve this problem with the assumption that the diode is on. So let's assume that D1 is off. Then I can write Vx is equal to, and I'm going to use superposition. So I'll have 2 volts times 3K over 3 plus 0.5. Okay. And then I have 8 volts times the voltage division of 0.5 over 0.5 plus 3, so 3.5. Let me rewrite that. that would be 6 over 7, okay? 12 sevenths of a volt, plus that would be 8, no, I think I made a mistake here. No, that's right, that's right, 12 sevenths plus 8 sevenths, all right, so 20 sevenths of a volt, which is going to be approximately, very approximately 3 volts, right? So, therefore, clearly greater than 1 volt, okay? Therefore, D1 is on, and my assumption here was wrong. So now let's go back to the problem and say, okay, if D1 is on, well, actually I'm going to redraw the circuit. If D1 is on, what do I have? I've got on the left side 2 volts, 0.5 kilo ohms, and on the right I've got 3K and 8 volts. Okay, and now the diode D1 is on, so I'm looking for ID, and this is sitting at 1 volt. Okay, so now I can solve this very easily, because I know that the voltage across here is 2 minus 1 volts. Right? I've got 2 volt source on the one side, 1 volt on the other side. Actually, what's going on over here, it has no bearing on the current that's going to flow here, because when the 0.5 resistor looks to the right, all he sees is the 1 volt between his right terminal and ground. So we're going to have, let's get rid of this. We will have 1 volt over 0.5, and so we'll have 2 milliamps. And flowing this way, we're going to have 8 volts minus 1 volt divided by 3K. So that'll be 7/3 of a milliamp. Okay, so therefore ID is going to be 2 plus 7/3 of a milliamp, or in other words, 13/3 of a milliamp. Okay, and that is the current flowing through D1. In exercise 4, we are asked to solve for the diode current using 4 different diode models, beginning with the most ideal 0-volt diode and ending with the Shockley diode. To begin, let's simplify our circuit by Thevenizing. The current source and the 6K resistor will turn into a 2 milliamp times 6 kilo ohm, or 12 volt voltage source in series with a 6 kilo ohm followed by a 4 kilo ohm resistor. We then add our diode. Now we can draw a load line just to get a visual view of what's going on. We'll have a short circuit current of 1.2 milliamps, right? That's 12 volts over 10 kilo ohms. And we will have an open circuit voltage of 12 volts. And our diode curve will actually be, it'll probably look like this. Because, let's see, no, I'm sorry, it's going to do this kind of a curve because it's voltage versus current. Something like that. This would be VD. Okay, I've drawn it on a V volt versus I curve. For the first case, I've replaced the diode with a 0-volt source, or short, and the current is trivially simply the 12 volts over the 10K. For the second case, we've inserted a 0.7 volt drop because it's a 0.7 volt ideal diode, so it would have the diode, let me draw the diode curve here. It would be like so. 0.7 volts. Okay, this is going to be, and might as well point out the first one is going to be like this. This is I. Okay. And so we will have ID is equal to 12 minus 0.7 volts over 10 kiloohms, or ID is equal to 11.3 milliamps. In the third model, we have replaced the diode with an ideal diode and a resistor and a voltage source. So 50 ohms and 0.65 is what we are given. And now we can write ID is equal to 12 volts minus 0.65 volts divided by 10.05 kiloohms. And ID is equal to 1.129 milliamps. Finally, we are asked to solve using a Shockley model, and we are provided with the voltage of the diode at a particular current. So that substitutes for IS. I'll show you that. And then N equals 2. I'd forgotten to mention that at the beginning of the problem, but I added that in. And I left out the C on the Shockley. So let's look at that. So what does it mean to have a Shockley diode that is 0.7 volts at 1 milliamp? Well, we have the diode equation. And during conduction, that's approximately IS e to the minus e to the plus VD over N VT. VT being thermal voltage. Right? Thermal voltage, which is about 25 millivolts or 25.2 millivolts at 20 degrees C. So we'll just use 25 millivolts. Now, if we can express the voltage for the diode in terms of the current, if you take the log of both sides, and that would be NVT times the log of ID over IS. Okay. Now suppose that we had 2 points on our curve defined, one at ID1 VD1 and the other at ID2 VD2. We can write VD2 minus VD1 is equal to NVT log, I'm going to do NVT quantity, log of ID2 over IS minus log of ID1 over IS. And we can combine the logs as ID2 over IS over ID1 over IS. And the IS's go away. So therefore we can write VD2 is equal to VD1 plus NVT log of ID2 over ID1. Specifically in our case, we can write VD is equal to 0.7 volts plus 2 times 25.2 millivolts is going to be at room temperature times the log of ID over 1 milliamp. Okay, so see, we don't need IS. IS is not needed. We could find IS from here, but we don't need IS here. Okay. So the solution for this version of the problem is going to be the intersection of the load line and the Shockley curve, which I've drawn here and zoomed in to show the intersection. And that the equality, or the intersection, is going to occur when we have 12 volts minus 10 kiloohms times ID that's the load line, is equal to 0.7 volts plus 2 times 25.2 millivolts times log of ID over 1 milliamp. Okay, so solve this for ID. Now we can do that graphically, or you can use your favorite computer program. I just want to point out, if we do this graphically, then, not graphically, iteratively I meant, if we go, let's say, clockwise, and we use current to calculate the load line, we get a voltage from the load line, and we project that voltage over to the diode curve, and from that voltage and the diode equation we calculate the current that corresponds to, and that would intersect the load line. And then we keep going around. Notice that this is not converging, but it's diverging. Okay, and that is because we are going from a shallower slope, the diode curve, to a steeper slope, the load line. All right, so what you want to do is you want to go from steeper, iterate from steeper to shallower slope. In this case, the slope of the diode curve is shallower than the load line, so we want to iterate from the load line to the diode curve, which means we want to go counterclockwise. I've indicated that on the IV curve here, and have labeled IV pairs, and so we will use the diode curve to calculate voltages from currents, and then we will use the load line to calculate currents from voltages. And we begin with I1, an initial guess. And we want to make sure that that initial guess is a current that is less than what we anticipate the current being, so that we're to the left of the intersection. We can make a rough estimate of the current by assuming that the diode has a voltage of, say, 0.7 volts, which you've done previously, and that gave us a current of 1.13 milliamps. So if I choose 1 milliamp, I think I'm going to be to the left of the solution. Doing so will get us a V1 voltage of 0.7 volts plus 0. So 0.7 volts. We then plug that into to our I2 equation, which is 1.13 milliamps. We'll plug 1.13 milliamps for I2 into our V2 equation, which gives us 705.7 millivolts. We plug that into our I3 equation, which gets us 1.1294 milliamps. Plug that into our V3 equation, yielding 706.13 millivolts. We plug that into our I4 equation, yielding 1.12939 milliamps. And we can see that at this point we can stop, right? Because ID is 1.1294 milliamps, and that's good enough. So it turns out in this case that our ideal diode plus or a constant slope diode right here of 0.65 plus 50 milliamps actually predicted this current quite well. Where was it? I missed it right here. Yep. So you might wonder, well, how good is this model? Let's think about if we were to change the resistance or the voltage source. Okay, so I'm going to resolve this one more time. So if we had a 1K instead of 10K, then the voltage plus resistor constant slope diode model would give us a current of 12 volts minus 0.65 volts over 1050 ohms, which is 10.81 milliamps. All right, the Shockley equation will, when solved, will yield ID equal to 11.18 milliamps, which is about a 3.3% error. Okay, so clearly we don't have as good of a fit here. Here's what's going on. I've drawn the load line for the case of 1,000 ohms, and I've drawn the diode curve. And out here is at 11.2 is the actual solution. But when we calculated or created our constant slope diode model, we created it based around the around 1 milliamp. So somewhere down here is where we found the slope to this diode curve, and when you extend it, which I didn't do too good of a job at, but it hopefully shows conceptually that when you extend it, where it actually intersects the load line now is 10.8 milliamps. Okay, and so therein lies the error, the 3.3% error. And as we go to higher and higher currents, or if we go far below the 1 milliamp range, we'll also incur increasing errors. So we kind of lucked out on solving a constant slope diode model using such a good model for our particular operating point. It makes the constant slope diode model look better than it is, but actually it is very accurate, perfectly accurate if you've picked the voltage and resistance right at the operating point where the circuit is actually situated. In our final problem, we're asked to use the circuit from example 4 and to find the small signal response voltage across the diode due to our current source, IG, having a plus and minus 0.1 milliamp perturbation or variation. And the first thing, of course, that we would do, had we not already solved this problem, would be to Thevenize it, which we have already done. The next thing is to recognize that we've been given some help here by telling us to assume that the operating point, or DC voltage across the diode, is 0.7. Notice that's capital V, capital D. So what we can do is, initially, we can replace V, the diode, with a voltage of 0.7. This here is our bias, or operating point, or we'll just call DC circuit. Okay, so all we're doing from this model is just finding what is that operating point current ID, and it's going to be the 1.13 milliamps that we have found before. We now want to draw our small signal circuit. For that, we will replace the diode with a single resistance, little RD. We'll keep the 10 kilo ohms, and for our voltage source, we will remove the DC voltage source, and we will replace it with a perturbed voltage source, which we need to calculate. So we have, recall that when we Thevenize, the voltage that we have, Thevenin voltage we have, is 6 kilo ohms times 2 milliamps. Okay, so now this voltage will be, okay, if the current source was going to be plus or minus 0.1 milliamps, then we'd have 6 kilo ohms times plus or minus 1 milliamp, which is going to be plus or minus 0.6 volts. Okay, so this is coming from the 6 kilo ohms multiplying plus or minus perturbation of plus or minus 0.1 milliamps. The response voltage, small signal voltage across the diode, is nothing more than just what is due to a voltage divider. So it's RD over RD plus 10K times plus or minus 0.6 volts. We need to find RD. RD, I won't derive it here because we've done it in previous lectures, is NVT over ID. We've been given an N value of 2. We're using 25.2 millivolts for VT because it's room temperature, that we assume, and our operating current we have actually found to be 1.13 milliamps. this yields resistance of 44.2 ohms. Sorry, 4.4 ohms. We plug the RD into our voltage division equation, and we find that VD, small signal, is equal to plus or minus 2.6 or 2.7 millivolts. So what does this mean? Let's go back to the beginning of what we were trying to answer. If I have a current source that is putting out 2 milliamps plus or minus 0.1, let's say it's sinusoidal. Okay, so this is 2 milliamps, and the amplitude here is going to be 2 times 0.1 milliamps. Then what we get out, or what we see across the diode voltage, is 700 millivolts plus or minus, okay, and this is not the scale, plus or minus, well, the peak-to-peak amplitude will be 2 times, roughly, well, 2.7 millivolts. Okay, so in the first case we did plus or minus 0.1 out of 2, or 1/20th, which is 5%, plus or minus 5%, and the response in the diode is plus or minus 2.7 out of 700, which is about plus or minus 0.4%. Okay, so in the usefulness of this is that, or the application, is that diodes are sometimes often used actually in electronic circuits to provide a voltage reference. So once you have them biased up and you're feeding that resistor diode circuit with a voltage, in this case the 12 volts, if we think of the Thevenin equivalent, if that 12 volts is coming, say, from a battery or from some power supply that could vary over some range, you see that the percentage of change in the supply voltage or supply current does not translate into an equal percent change in the diode voltage. In fact, it's far less. And so you can have a voltage that is a reference voltage to be used however you want in your circuit that is fairly immune to changes in the supply. And that is actually an important need in electronics. Having voltage references is very important. And we'll see more of that perhaps in the rest of the course. As a final comment to this problem, you might be wondering whether we sacrifice something by simply using the approximate voltage across the diode, DC voltage across the diode of 0.7. If we had not been given that, but we were told instead it's an N equal 2 diode that is 0.7 volts at 1 milliamp, what we would have had to do would have been first to solve the DC circuit, which we have done previously up here when we solved it for using the Shockley equation, case 4. And we would have found the current was 1.124 milliamps, and then we would have found that the voltage, instead of being 700 millivolts, was 706 millivolts. Right? And then you ask, well, how would that actually change the small signal response? Well, what it would have changed would be that in our RD right here, instead of using 1.13 milliamps, which came from assuming a 0.7 volt diode, we would have had 1.129 milliamps, right? That would be the more precise answer. When you plug that in, we would have had a slightly larger RD, 44.45. Point is, it would not be a significant difference. So when you're doing small signal analysis, a lot of times you don't need to have the exact operating voltage. You just want to be in close vicinity. Now, that depends on what you're driving your circuit with. In this case, because it's being driven by 12 volts, the current that flows is due to the voltage differential across this 10K. That voltage differential is the driving voltage, a large voltage of 12, minus the diode voltage, which is a small voltage. And so we can get away with just approximating VD, because if, after all, VD changes, say it's 0.65 or it's 0.75, that's only a change of 50 millivolts out of approximately 11.5 volts that are going to go across that 10K resistor. It will not produce a significant error. If we were to repeat this problem with a, say, 1.2 volt source or a 4 volts or something smaller, then we would find that having an accurate operating point voltage for the diode becomes more important, because that uncertainty in the diode voltage becomes a larger percentage of the net voltage across the 10K resistor, which in turn translates into an uncertainty or an error in the operating current ID.